Hi everybody, woo, welcome. It's another Ask an Astronomer for September 17th, the day after my birthday. Let's see if I can make it stop doing that. Why? There we go. That's what I want. So let's go home here. How's everybody doing? I thought that the last couple times have been really fun, and I thought that I would do a kind of more grandiose one. I think I'd mentioned this last time, but I thought I would do a session today about the Big Bang and the origin of the universe, which would be kind of fun. I'm also right now dog sitting, so there might be a moment where a dog comes in. I mean, you won't see the dog in here. The dog will be down in this direction. But like, if that happens, I'm gonna have to maneuver the dog out of the room because the cat does not like the dog. It's not a huge deal. The dog just sometimes comes on in. So the last time we met, we talked about telescopes, and we ended up talking about James Webb, and we talked about very distant galaxies. And I thought that, something I haven't talked about since I started this was the kind of bigger picture, the whole universe, right? And so this is a subject called cosmology. I'm not a great cosmologist, but I'm all right. And I do deal with things that are very far away, but not as far away as the stuff that we're going to be talking about today. And so I wanted to start here in Space Engine. Let's set it to now, normal time speed and current time. And so if we set it to now, we can kind of, oops, that's not what I want to do. We can orbit our way around the planet. Europe here is in the dark. Let's get ourselves right here in the Sahara Desert. Right here in the desert. So if we're in the middle of the desert, we look up at night here. We see the night sky, and we can crank up the brightness in the night sky a little bit. So we can really see, whoops, so we can see some stars. And now here's the question that I wanted to start with. Ooh, got a really nice Milky Way right here. So this is like, imagine like an incredibly dark sky, clear night. Probably will never see that good. But let's imagine you're outside at night, you're looking up at the stars, and you're wondering, and you're looking at these things, it's really beautiful. Here's a question that people have wondered, for a long, long time, and you may not have wondered it, and that's fine. It's the idea for hundreds of years. The idea of, why is the sky dark at night? Why is it dark? Why, when I look here, is it dark with some stars? Why is it dark? Now, maybe you think that you hear that question and you go, well, Kevin, it's dark at night because the sun's gone. And that's a pretty good answer right now. Like, pretty makes sense because it's dark, like during the day you can see the sun. But the question that why this was brought up and why this is a question is because when we started understanding the universe and understanding the fact that there were these stars, and when we started building telescopes and looking through telescopes and seeing that we could see stars between the stars we could see, right? Like, you could imagine like thinking, well, these are all the stars, and then going, well, let's just look through our telescope so we can, and as we look through the telescope, you start seeing more stars, right? You see those little stars popping out, and if you keep going in, you're like, well, there's even more stars. Between any groups of stars, there's more stars, right? And like, if that's the case, if between all the stars are more stars, then why is it that the sky is not completely bright with stars? And so there's this famous, there's like an animated GIF on the webpage for this, which is called Olber's paradox. And if we turn on this in a second, we can show you this. You could imagine that we've got the sun, or and between the sun and other stars, and over time you get other stars, and in between those other stars, that are, And so why is the sky not just like that constantly? Why is it like, dark, like we see in Space Engine, and not just completely and utterly filled with the light from stars, beyond stars, beyond stars, beyond stars? And so, like, maybe you say, well, okay, the reason is that things that are farther away are fainter. So if I had a candle and I took it really far away, it'd look really, really, really faint, very hard to see, right? So maybe that's the case. And this is true. Light from a star, its brightness gets dimmer and dimmer as it goes away. by a factor of what we call 1 over r squared, meaning 1 over the distance from you squared. So as you go twice as far, it gets 1/4 as bright. If you go 3 times as far, it gets 1/9 as bright, right? You square that number of how much times farther, and that's how much dimmer it'll get. That's true. The problem with that is that as you do that, as you get farther and farther away, you're actually, each little patch of sky you're looking at, where yeah, any star that was in that's now farther away, farther away it's fainter, but the patch of your sky encompasses a larger region farther and farther back, right? So like, if I'm holding up this right here in front of me, but if I like move this away, the in my own, I guess we'll do here, right? Like if you imagine like some here, but if that's gonna be really hard to do. But if you hold your thumb up, your thumb in front of your hand or whatever, that's like a tiny bit. But if you take your thumb away, now my thumb is, like my microphone is covered by my thumb. And if I like look farther, it's like smaller and smaller things. This one region of the sky, some patch in the sky here, like, some patch that we have like between these stars, that patch of the sky for things that are close by encompasses a certain size. But as you go farther and farther and farther away, it encompasses a larger and larger and larger size, right? And it's the same factor. And so the way to think about it is, even though the light gets fainter from farther objects, in that patch of sky, if stars are randomly located, there's a square as many objects, which means that they balance each other out perfectly. The faintness of stars and the number of stars going up as you look at the same patch that goes farther and farther out. So this is called Olber's paradox. Named after, probably not the person who discovered it, first thought about it. It was probably first thought about by quite a few people, like in ancient Greece, and I bet that there were probably Arabic astronomers and things who also thought about this, but didn't write it down in the same way. But, this guy, Heinrich William Olbers, described it in 1823, and that became, the famous way that now it's described, which is, why is the sky dark at night? If you go and look at the sky, you should just see star after star after star. Every way you point should point to a star, and over a long period of time, that star's light will have gotten to us in which we should see it. So the sky should be completely uniform with brightness at night, which it is not. And maybe you think, okay, well, there's dust. Dust will block the way. Well, if the dust gets hit by the light will then heat the dust up, and the dust will then glow. So, no. So, oh man, there's a pretty good, I wonder if I can, do I still have it open? There's a really good description of my goofy attempts to try to describe sizes here. If I do this right here, and then I open up my internet again. Dink. So here, you can see that, let's not drag that. Let's, I hate that OBS makes you drag all kinds of stuff, but like if I drag this, you can see here that like the observer's looking here, and then this is 1 unit away, there's 1 star, and then 2 units away, all the stars are 1/4 as bright, but now there's 4 of them, right? Because it's the same patch, it's just, 3 units away, the stars are 1/9 as bright, there's 9 of them. 4 units away, everything's 1/16 as bright as this star, but there's 16 of them, which means it's just they balance each other out perfectly. Ba-ba. So, what's going on? We've got this really crazy thing where the sky is dark at night. And the person who is commonly thought of as the person who understood and like first proposed what was going on was, of all people, and this is like a real fun little factoid for you, Edgar Allan Poe. Yes, Edgar Allan Poe, father of the modern crime story, horror novelist, poet, Nevermore, Raven, etc., etc., etc. And he said, you know what it is? What if the universe isn't, like, what if we're not seeing all the way out to the very, very edge of the universe? What if we're only able to see out to some edge, and so therefore there's not infinite stars that we're seeing out there. The stars take a while to get their light to here, and, the universe is finitely old, he said, meaning that the universe had some sort of, like, beginning, and there's not enough time for lights to have gotten to us from the farthest stars out. So the reason we don't see the faraway stars and the sky is not uniformly bright is, there's still light coming from us, meaning that in an infinite future, eventually light would come from us. So that over the course of time, light would continue coming from us, but providing stars didn't die, right? And like, that turns out to be one of the earliest ideas of maybe the universe having some sort of start was the solution to this paradox. I guess it wasn't the early. There's a bunch of other people who've thought about this, but it's one of the more correct early ideas, the solution. And it implies a beginning of the universe, which is pretty cool, right? So let's take and put that aside, the idea of a beginning of the universe, and let's think about another way we can think about the beginning of the universe, or what implies the beginning of the universe. We can start thinking about the modern idea of why we think the universe has a beginning. And it comes from a guy named Edwin Hubble. And so now if we go back to Space Engine and we search for Andromeda, which we can fly towards here. Oh gosh. Let's make sure we have, whoa. Reset the zoom there. That was pretty intense. So here's Andromeda. Andromeda was observed by people for quite a long time. You can see with your naked eye from a very faint, from very dark area. But one of the cool things that Edwin Hubble did was that Edwin Hubble actually looked at this and determined that there were stars in this that were what he called variable stars, or Cepheid variable stars, which are a type of star that varies in brightness over time, gets brighter and dimmer and brighter and dimmer. And so Edwin Hubble goes and looks at this, and he does this for a bunch of stars. And why that matters is because these stars, they get brighter and dimmer and brighter and dimmer over time. You can tell from how fast they get bright to dim to bright to dim. You can tell how far away they are by telling, because that'll tell you how bright to dim, how the speed of which they do that, the frequency to which they do that, is related to how bright they are intrinsically. And so Edwin Hubble knew, here's how bright these should be. Instead, they're this bright because they're really far away. So he compared those two numbers and said, this is how far away these stars are. It'd be the equivalent if I set you in a dark room and I shone a light in your face, and then you're like, what light is that? And then I said, it's a mag light. Or, depending on the light I told you it was, you would then go, okay, if it's this intrinsically, and I know how bright that is, like if I said it was like a spotlight or something like that, you'd be like, wow, that's really bright, but it doesn't look that bright, from your room. It must be far away. You do this, your brain just does this automatically. It just says, here's how bright I think this thing should be, and here's how bright it is, so I can tell distances to it. But in astronomy, it's a little tougher because it's really hard to tell intrinsic brightnesses of things, because stars have generally a lot of range of brightnesses that we talked about. But with these variables, you can do that. And so Edwin Hubble, the main takeaway is that Edwin Hubble looked at this galaxy here and a bunch of other galaxies, and he said, I know how far away they are. And when he did that, he said, what's also really interesting is that as I look at galaxies, I can also tell you, based on the light that they give to us, and how the light that they give to us is shifted in wavelength to redder wavelengths, that most galaxies that I look at are moving away from us. And they're moving away from us at a speed that's related to how far away they are. Meaning, the farther away the galaxies are that I'm looking at, the faster they're moving away from us. And he created a law that we call the Hubble Metro Law, because of two scientists, Hubble and this guy Georges Lemaitre. And this is a pretty profound thing. Georges Lemaitre pointed out something really incredible about this. If this is true, and that every galaxy we see in the sky, of which all of these are dots, are galaxies, right? We're not like the Milky Way, all the stars that we talk about is somewhere back there. Where is the Milky Way? Right there, right in the very center. There's the Milky Way. We can crank up the brightness and remember 2+. There's the Milky Way, right? So we're over here at Andromeda, but there's the Milky Way. But everything here is, every dot is a galaxy. If every dot as a galaxy is moving away from us, then that implies that you could take that velocity, that speed of things moving away from us, and turn it backwards. What does that mean? Well, Edwin Hubble discovered that the universe is what we call expanding. And I'll talk about that, what that means. What that means is that it can be thought of as either the galaxies are all flying away from each other, or space itself is pulling the galaxies away from each other. They're equivalent. But what from our point of view, every galaxy we look at is moving away from each other. And from our point of view, it looks like it's moving away from us. The reason that we think that is not because we're at the very center of the universe, but rather because we don't feel ourselves moving, because you can't feel yourself moving. You can if you're accelerating or decelerating. That's, physics. But if you are floating through space at a constant velocity, you can't feel that motion. And now the universe is accelerating in its velocity, but it's not something we can feel. It's very light. But essentially, what it mostly is that we preference our position as the at rest position because we're very vain. But if you're sitting over here, and this is why I brought us over to Andromeda, if you're sitting over here in Andromeda and you were to fly into Andromeda and like sit from Andromeda and look at all the galaxies from Andromeda, they would all also seem to be flying away from us, or flying away from you here in Andromeda. Every one of them, which is pretty ridiculous. If you were to go to a really distant galaxy, I guess this is the Milky Way, right? We can go to, let's go to pick a really distant galaxy like this one right over here. There, and that's a star. That's not what I want to do. I want to go to galaxies. Let's like really get out there. There we go. Let's go to a really distant galaxy like that one there. So now we're at like some distant galaxy. Here we are. Galaxy RGO 451146, right? Lenticular galaxy here. You can see it's lenticular. It's not really super spirally. It has some spiral structure, but not really high spiral arms. If you were in a star in this galaxy, all the other galaxies you see around, all of them would appear to you like they were moving away from you. All of them. Every galaxy would be moving away from you. And that's just because you think you're at rest. And so it's a thing where if you're on the ice and, you know, like everyone was moving away from you, you'd feel like, oh, everyone's moving away from you. But then another person would be like, everyone's moving away from me as well. We all feel like we're moving away from each other. And you could think of it also as the space between the galaxies is pushing them all apart from each other. Now, that's a big, complicated thing, especially because most people ask then, well, why is our planet, am I moving away from other people? We're held together by forces that are so much stronger than this expansion in the universe, which we call the Hubble flow. It's a it only really operates on galaxy scales and not even on, like, the Andromeda and the Milky Way are actually coming towards each other because gravity has pulled them together, because gravity is stronger than this Hubble flow. But on large, large scales, where galaxies aren't pulled very strongly by gravity from each other, they're just moving away from each other by the expansion of the universe. And that expansion of the universe was set in play at the beginning of the universe. And Georges Lemaitre said, well, let's look at the expansion of the universe and think about it and then turn it backwards and say, well, that implies, if we know the velocity of all the galaxies this moving this way, it implies we could trace it back to 13.7 billion years ago when the universe must have started. By the way, this is kind of a fun thing. There's nothing on the screen. It's not that exciting. Let's really crank up. There we go. Much better. I guess we can go home. A guy named Albert Einstein, when he was looking at the universe and thinking about the fact that the universe was filled with galaxies, right? He was thinking about it and he thought, you know what? At the time, everyone thought, this was before we understood that the universe was expanding. So this is between 1900 and 1920. He thought, if the universe is filled with things, and he started doing some math, well, then gravitationally, those things should pull together. And so either the universe should be contracting or expanding. And at the time, that we hadn't discovered the universe was expanding. Because like gravity should either pull them all in or they should be moving away from gravity, like gravity that wants to pull them all together. Things should be pulled apart. But the fact that the universe existed to Einstein was confusing because gravity should just have pulled everything in together. So either it was in the process of doing that or everything was moving away to resist that. And so he goes and writes all these calculations, and as part of this, he does something that he refers to as his like greatest blunder. Hello, Splendid. Hi, Cheetah. So what Einstein does in this is what he calls his greatest mistake or his greatest blunder or whatever, is he cheats. He says, well, the universe isn't expanding or contracting, because he did this before Hubble did his discoveries, like in the early 1900s. He said, the universe isn't expanding or contracting, so I'm going to put a thing I'm going to call a cosmological constant. We call it cosmological constant. Something that like resists the pull of gravity, keeping the universe steady state, essentially everything as it was. And at the time, we thought the universe was infinitely old, that it was just in this one state. This is just how it always has been. And had no beginning. And when Edwin Hubble made his discovery the universe was expanding, he was like, oh, phew, I don't have to, I can take that constant back out. It was as if the universe saw that Einstein had kind of cheated and said, Einstein, you didn't cheat, and pulled that out. What's really charming, though, is that, and I'll talk about this in a future episode, is that the universe is actually accelerating its expansion. And so the way that we can describe that in Einstein's equations is by taking that cosmological constant and putting it back in. But that's for another time. But all this, the Hubble law, that the universe is expanding, this actually implies that the universe started somehow. And in the 40s and 50s, people started looking at this idea that the universe started from something. And these, and like, that was really, for a lot of scientists who thought the universe was infinitely old, was really like the universe couldn't have started from something. That's absurd, right? And like, in the 1949, this astronomer named Fred Hoyle was on the radio, and he was like trying to make fun of an idea, this like theory that the universe started from something, and like Georges Lemaitre's idea that the universe must have started from this primordial atom, this thing where the universe if you trace this expansion backwards, it came from one point or whatever, like. And Fred Hoyle went on the radio and called it like, well, that must imply like some sort of Big Bang or something like that, as like a mean like joke, because he was the person who proposed the steady state theory. And that is what, because it was this guy named Gamow proposed a theory that we now know as the Big Bang, and it was Hoyle making fun of it, which is why we call it the Big Bang. And it turns out that is, in fact, what we think is going on, what we think happened. Which is that in 13.7 billion years ago, the Big Bang happened. Now, you might ask, where did it happen? And the thing is that you shouldn't think of the Big Bang as a thing that happened someplace. The universe is infinite in every direction. If I point in one direction, another direction is infinite. Infinite. And it's filled with galaxies. We only can see part of it, which we'll get to in a little bit. But it's infinite in all directions. And if you trace backwards the Big Bang, backwards the expansion of the universe, then all the space between the galaxies shrinks down. And so what the Big Bang is not a place, it's actually a thing that happened. It's an event that happened where the entire universe was essentially infinitely dense with stuff. And in that infinite density, this expansion started happening. It wasn't an explosion, and that was what we generally referred to it as. That was what Fred Hoyle referred to it as. But it was this expansion. Something set in motion this expansion. And here's the big questions that people have about this. What happened before the Big Bang? What caused the Big Bang? What is the universe expanding into? I can only answer a couple of these questions, but not really. What caused the Big Bang? We have no idea. Astronomers, scientists have no idea. There's theories. But the theories are speculative, incredibly speculative, because it turns out we only can see what's in our current observable universe. And so maybe people think that there was another universe that died, and in that process our universe was created. We don't know. Maybe it's biblical. Maybe God made it. Maybe we're a simulation, in which case it was created in the instant of running the program. I don't know. And speculating on that is fun. I can't tell you, though, what happened. In fact, I can't tell you what happened in the Big Bang, for a few, milliseconds. There's a tiny bit of time with which no astronomer or scientist or physicist can tell you exactly what happened, because physics, the rules with which we govern the universe, time, don't make sense. And so really, there's no before the Big Bang, because time started when the Big Bang happened. In fact, a little bit afterwards. I guess there was no afterwards. It had to start when the Big Bang happened. So whatever started the universe in this Big Bang, what happened, we don't know what, and it started time. So there is no before the Big Bang. And then on top of that, it's not that the universe is expanding into something. The universe is everything. The stuff inside of the universe is just expanding away from each other. All the galaxies are expanding away from each other in the infinite universe. So it's not a thing where it's like a balloon that's slowly inflating into a room or something. Or sometimes you see a metaphor of a raisin loaf where the raisin loaf is rising in the oven, and so all the raisins are moving away from each other like galaxies. But you're thinking, the universe must be in some big oven. No. The universe is everything. It's infinite. And it turns out we don't have the ability, scientifically, to explore what's outside of that universe. If they're to explore what's, when I say outside, I mean theoretically outside or another alternate universe. We don't have the ability to look at that right now. So I can't answer those questions. These are the big questions people ask me all the time. I'm sorry, I always have to tell them there's no before the Big Bang because time didn't make sense. There's no such thing as before the Big Bang. all I need to say is that the Big Bang essentially happened, and like in the first like tiny bit of cosmic time, which we call the Planck epoch, like this incredibly tiny bit of time where the universe is essentially just energy of expansion, and the universe is expanding and things are moving away from each other in an incredible rapid way. And so you may have seen pictures that look like, let's see, this right here. Let's bring up this picture here. Look like this. This is your famous picture of the universe expansion. I'm going to move myself over here, and I'm going to stand over here. Oh, dog is coming in. Daisy, you need to leave, Daisy. You're going to make the cat freaked out. Daisy.
Daisy, come here.
Well, so this picture is interesting here because it's a representation of the universe's history over time, but also physically how it like got larger, and when I say the universe, I mean everything within the universe. So if we look over here, you can see that on the bottom it has like 10 to the minus 32 seconds, 10 to the minus 30 seconds, 1 second, 100 seconds, 1 year. Like the Big Bang happens at 0 here, and then when it says 10 to the minus 32 seconds, this is like an incredibly tiny fraction of a second, right? And I could give you these numbers, but they'll just go in and out of an ear. You can go look these numbers up yourself. They also change depending on what source you're looking at. But know that I'm talking about fractions of a second. And essentially, the history of the universe post-Big Bang, once time starts, physics is totally different. And for a fraction of a second, the universe physics is not even understandable. Like all our math that we do in the modern world, the universe of physics, if you try to do that math and extrapolate back to that time, you get a lot of divide by zero errors. It doesn't really work the way you want it to, which is bad. So we can't explain what goes on before then. So anything could have happened then, right? So that's where God could live. God could live in that tiny bit of time. Let there be light, essentially, because that was what happened initially. Was that the universe, in its early stages, it was just totally and utterly different from anything like that we have in our universe, because our universe wasn't that dense and hot. If you take the universe and increase its heat and density, and heat, meaning the particles and everything, or the substance or whatever's in it is moving that fast, and it's that dense with stuff, things get pretty weird. So this is a picture here showing the time after the Big Bang, again in 10 to the minus 43 seconds, 10 to the minus 35 seconds, 10 to the minus 12 seconds, and the fact that the universe's forces, there are 4 fundamental forces in physics. There's the force you're super familiar with, gravity. Gravity is the one that you probably hang out with the most often. You don't realize that you also hang out a lot with electromagnetic, but gravity is the one that like keeps you on the planet, keeps you, if you throw a ball in the air, you can count on gravity. It's also the weakest of the forces. And electromagnetic force is the force that deals with light. It's also the force that deals with, the fact that if I take my hand and touch my hand, like I can't put my hand through my hand, is because of electromagnetic forces. You're pretty thankful for the strong nuclear force here, because the strong nuclear force is the force that governs the way that atoms are bound together in their nuclei. Pretty important. If the strong nuclear force stopped, all atoms would just separate apart in an incredible explosion of energy, which would be bad. And then there's the weak nuclear force, which is a force that governs radioactive decay, and I don't want to get into that too much. But if you take the universe and you make it hotter, so you can see the temperature of the universe right now, 3 Kelvin, which is very low. It's 3 degrees above absolute zero. It's the average temperature of the universe. And you slowly raise the temperature up, and you make the energies of the particles a lot higher. You get it up. These forces, we think, unify together. Meaning that at the beginning, there's this grand unified force, just one force. And then as the universe expands, it cools off, and the forces separate out from each other. So you can see the gravity separates out first, and then later the strong and the weak nuclear force separate out from these other forces. Now, some of this is speculative because we can't mathematically right now combine these forces, but at some point we will. Like, these are what physicists are looking for, is this grand unified theory that unites all this, right? And there's physicists who are way smarter than I am who are working on things like this. But mostly I just want you to know that the universe is going to go from a point of very hot to cooler and cooler and cooler. And as that happens, things get fun. because when it's really hot, it's too hot and there's not enough time for things to happen. And so you get this like incredible, weird, unified force like of light that, which is mostly just pure energy. And then over time, like the forces come out from each other and you start having this thing happen where the light is in a situation and the energy is in a situation that from that energy we have we call quark gluon plasma. Some weird substance is formed from that energy. The energy turns into subatomic particles that can kind of like live in like a plasma of like weird, like it's just the universe is filled with this. And from that, as the universe cools eventually, because of these forces that are separating out, you start to get the earliest actual particles that come from this. And what's really cool is there's this thing called baryogenesis that happens. The idea of particles like the particles we know of, the particles in the periodic table, they were formed from this initial soup of universe plasma, this quark gluon plasma. And that soup, when it created particles, it borrowed from the energy and created particles. It preferentially created the particles like we have. But when you do this, when you borrow from energy to make particles, you generally tend to make them in particles and then what we call antimatter particles. Attempting to reconnect it. Okay, so now hopefully I've reconnected. Okay, good. So I'm back. Woo! So, as I was saying, if you take energy, you can borrow from the universe's energy to create particles and antiparticles. And if you do the opposite, you can take particles and antiparticles and put them in and get energy out. And the idea of borrowing from the universe to make particles and antiparticles, what that mostly just does is it just like creates an equal amount of particles and antiparticles. But we're all particles. So where's the antiparticles? Well, something must have happened, and scientists have some theories, but don't really understand, that preferentially chose particles over antiparticles. And you're saying, oh, why? Well, poor antiparticles, that's weird. But like, if it were preferentially chose antiparticles, we would have just called those particles and the other one antiparticles. We're just, just like north was called north and south was called south because the people in the northern hemisphere, like, lived there and thought they were more important. If, like, we were conquered by people from Aboriginal Australia, they would have said that was the Northern Hemisphere and maps would be upside down, which is pretty cool. If you've never looked at a upside down map, like where they've taken all the words and flipped them upside down, it's wacky. Your entire sense of like where things are on the planet is like really fun. Anyway, so that happened in the early universe. As all the forces were, freezing out from each other, because the universe is cooling, you're getting particles preferentially over antiparticles. And then another thing is happening, which is that the universe has to inflate. So let me explain that. When astronomers, actually, let me back up. I'll get to inflation in a second, in like a little bit. As the universe is all the things are expanding within the universe. That's what I should say. The universe is expanding, but things are expanding within the universe, and you're getting the early particles. Eventually, there's a period of time where the universe cools off enough that these early particles get cool enough that the earliest particles, which are protons, electrons, they in an early universe are too hot. They just want to But eventually, they realize like, the universe is cool enough now that we can, because of the electromagnetic force, we can combine to make atoms, like hydrogen. And when that happens, when you get these atoms of hydrogen, light then is freely allowed to travel. If you take a big box of just protons and electrons that are so hot that they're just all flying around each other, light ping-pongs around that. And so light can't travel through it very far in straight lines. So it's like looking through, smoke or something like that. Light just bounces around. But once the universe cools off, which happens like 100,000 years after this Big Bang, then the light can travel, okay? And I tell you this because when the Big Bang was proposed, the scientists who thought of this said, well, if the universe was that hot, this hot, and cooled off, then that implies that it's some temperature today, which would mean that hypothetically, we should be able to see light left over from the Big Bang at a certain temperature. We should be able to look in the universe and see leftover light that has been traveling from the Big Bang, and it should have a specific temperature, which is like a crazy prediction to make. Like, what? Light left over from the Big Bang? And so, at Princeton, there was a famous set of astronomers, Wilkinson and, gosh, let me see if I can remember these. So the cosmic, like, in the late 40s, a guy named Ralph Alpher and Robert Herman predicted this, and then, there were some other guys David Wilkinson, in the 60s, David Wilkinson, Peter Roll, at Princeton, started creating a telescope so that they could find this. It was predicted by people for many years. They said we should look at light and the radio wavelengths, which is pretty long wavelengths we've talked about. We should make a radio telescope to look for this leftover light from the Big Bang. At the same time, down the freeway is this. This is a horn antenna. This is a telescope. Light comes in here, and the detector's over here, and it bounces in here. It's radio light, so it's not like a telescope that you might have ever seen. And you've got these two dorks, and the names are Penzias and Wilson down here. What are they? Arno Penzias and Robert Wilson. And they're at Bell Laboratories, and they build this telescope because they want to look at at satellites and do radio astronomy, and if you've got a radio telescope, let's look at some radio sources in the sky. Let's look at satellites which are giving off radio light. So they build this thing, and the first thing they observe is pretty neat, but there's this noise level under the observations, and they get frustrated, and they go well, okay, there must be some part of the sky there that's giving off these noise. Let's point at a different part of the sky. Same thing, like a hiss. Like if you were watching a TV show and there was just some zzz under the whole thing, and you'd be like, well, change the channel. Maybe it's just that channel. And you change the channel, same zzz, change the channel, zzz. What's going on, right? And they go, you know what it is? They look in the telescope. They go look in this horn. They go walk over and they climb up and they look in here. And there's a whole bunch of pigeons in there. And they, let's just say they shoo the pigeons off. I think that if you read the paper, it's not as nice. But these pigeons, they claim, have given off what they call a dielectric substance, which is pigeon poop. And they pooped all over the inside of this telescope. And they shoo the pigeons off. It turns out some of the pigeons are homing pigeons. They come back and roost again. They have to deal with this a couple times. And they go, okay, that was what was going on. We had all this pigeon poop, and the pigeon poop was causing weird reactions and giving this hiss. And it explains why, no matter which way we were pointing it, we would get this pigeon poop sound. Once the pigeon poop's cleaned out, no pigeons, they do it, same thing, zzz, zzz, every direction. And it's at that point that they call up their buddies at Princeton, these other people at Princeton, Wilkinson, etc. And they go, I think we discovered something that you are about to build a telescope to look for. Because these scientists, had published things on this. I think that we discovered this leftover light from the Big Bang. And the Princeton folks were like, yep, got the phone. We're like, we've been scooped. And Penzias and Wilson win a Nobel Prize for this discovery, even though oh no, did I disconnect again? I shouldn't be. I should be fine. It says that I'm doing all right.
Princeton folks.
Nope, I'm doing fine. Never mind. Okay. Whew. And so this in the journal there was a thing. It was an article that was on the discovery of this 2.7 Kelvin background radiation, and then the next article was an article from the Princeton folks explaining what it was, explaining that it was in fact the leftover light from the Big Bang. It's still light that's around. Some of it's falling on you right now. If you ever used an old television that had static, some fraction of the static that your television picked up, that you were seeing as just static on the TV, some fraction was leftover light from the Big Bang, which is incredible. And it was years later when we built this thing called COBE, and COBE was the Cosmic Background Explorer, because we called this the Cosmic Microwave Background. Cosmic because it came from the universe. Microwave because the wavelength you had to look at this was in the microwave wavelengths. And background because it's underlying all of the light you see from stars and stuff. It's just everywhere. And the cosmic microwave background, we built this telescope, scientists built this telescope called COBE, and they put COBE up with an instrument called Derby. And COBE and Derby went to go look at the cosmic microwave and measure exactly what temperature it is in all directions and average that. And so they came up with this right here. This is a very, very cool thing if you've never seen this before. And what you're seeing here is this is the frequency of light and this is the intensity of light. I should flip my thing around. Whoa, it's really hard to move with my left hand and also do this. Frequency of light and the intensity of light here. And what you're seeing, I should just bring up the giant arrow instead of doing this. It's much easier than moving my own self around. What you're seeing here is you're actually seeing that these red dots are the data from COBE, and this blue line is the fit to those red dots. It's actually not a fit. It's just the prediction of what the universe should be compared with these dots. You can't even see the error bars on this because they're so tiny. Generally, they have to increase the error bars by quite a bit. This is essentially astronomers calling their shot in the 70s, saying, if the Big Bang happened, the universe should be this temperature, given by the blue line. This is what the universe's temperature should be. We go in to build a telescope. We put the telescope into space. The telescope gives the data back. We plot the red points and the blue line. They fit perfectly well. Let's see if I can find Ned Wright CMB. I want to find his... Yeah. This is another picture of it here. Ned Wright is the person who was the person who first plotted this from the COBE data, I'm pretty sure. Where is his... Oh. Hi, Daisy. You shouldn't be here, Daisy. Daisy. I'm bummed that I can't find it. His website used to have this. CMB email. COBE. Maybe I shouldn't do this live, but I just can't find it. But anyway, Ned Wright sent this email about this. I've analyzed it by taking a linear, the results are presented here. They're quite consistent with the unbiased. There's probably a real quadruple. Essentially Ned Wright was the person. And I bring up Ned Wright. Why this guy? This is Ned Wright, by the way. I bring up Ned Wright because he's the person who first taught my cosmology course. I'm gonna kick this dog out. Sorry, Daisy, you gotta go. You're scaring the kid. Thank you, though. I appreciate you coming by. It's very nice of you. What a good doggy. And so if this ever gets back to him and he sees how badly I'm butchering my cosmology, he'll be very disappointed because he taught me my cosmology class. He's a very, very good, prominent cosmologist, and you can read his FAQ on this. It's fantastic. But this was one of the great discoveries, right? And it was years later that we made a map. You may have seen this map before. This is a map of the cosmic microwave background. A map of the cosmic microwave background radiation. And what does that mean? What does a map of the cosmic microwave background radiation mean? Well, it means if I point a telescope and look at all areas of the sky, and I look at it and see if there's any differences, right? Any little patchy differences. And what you're seeing here is where it's redder, that's an area of the sky that's a little bit hotter in that direction. It's a little bit hotter over here. It's a little bit colder in these dark blue areas. And why that matters is because this is light left over from just after the Big Bang, when light could travel through the universe, 300,000 years after the Big Bang. So what this is an imprinting of what the universe was like just after the Big Bang. This is a representation of the baby picture of the universe. Meaning, this is telling you in all directions that the universe is fairly uniform, because these little tiny blips are magnified, enlarged to show texture, essentially. This is so perfectly smooth just from that last plot. what you're seeing, this last plot shows is pretty smooth. But like, if you just take what little tiny differentiations there are and like make them look larger so that you can see them, that's what you're seeing here. And this is like such a beautiful and important thing because it tells us about the early structure of the whole universe. And the fact that 300,000 years after the Big Bang, you had large structures like you're seeing here. Big structures and, gaps of structure as well. Because everywhere where it's hotter, it's more stuff. There's more what we call dark matter, which I don't want to get into in this video. But essentially, this is the baby picture of the universe. And over time, we've done better and better with it. This is a picture here where you can see that COBE couldn't do very well. WMAP, the Wilkinson Microwave Anisotropy Probe, did better. Wilkinson named after one of the Princeton astronomers. And then Planck, which is a European telescope, did even better than this. Really, really nice fine grain here. And that's like great because the better detail you have on this, the better understanding. And this right here is not proof. There's no proof of the Big Bang. It's a theory. But it's incredible evidence. It gets better and better and better of the Big Bang being a thing that happened because this is exactly in line with what we expected to see from when we were first looking at the Big Bang as a theory. Like, oh, it should be this, and here's how this works. But this brings up another question. If we bounce back over here, there's Planck. This right here and this right here are in opposite parts of the sky, meaning we're looking at the universe as it was in one direction and another direction, one direction and another direction. These parts of the sky are very far away from each other. Very, very, very far away from each other. And it turns out that if you look at the way that things are in this direction and this direction, they're very similar. They're almost the same temperature. They almost have the same type of clustering. It's consistent no matter where along the curve you take the differentiations. Yeah, so this curve is a slightly different representation. You don't look at this curve. This curve is just like I guess how do I describe the CMB subtraction? I want to show you that what I mean. If you have the CMB, you have to subtract out this is a more raw CMB where you have to worry about microwave sources from the you have to do a bunch of subtractions of stuff. These are the WMAP CMB fluctuations here. So this right here is the raw CMB from the telescope. And that green is essentially why this is so smooth, is because that's the green. If you subtract that out, if you subtract this thing out, what you're left over with is this, which, you still have some, you're subtracting out just the overall green color and you're saying, okay, well, what's the little tiny weirdness on top of that? And you subtract that out and now you're left with this, which tells you that the Earth is kind of moving in one direction compared with the other. Well, this galaxy is moving one direction. All right, so you can subtract that out and you're left with this. And then you're like, okay, well, what's this red bullshit? And the red bullshit is the fact that the galaxy has a lot of weird microwave stuff as well. So you make a map of the galaxy and you subtract that map out and then you're left with the version you see here, right? And so I mean, you could be more specifically with these WMAP ones because I think this might be the Planck version, but this is the universe is overall very smooth. These are tiny fluctuations on top of that. But this introduces the idea here that in any direction that we look, we saw the same smoothness. The properties of the universe in that direction, the galaxies we saw, the things we saw were the same as the other ones over there. And the equivalent is if you had a potluck and you said to the potluck people, I'm only going to give you 10 minutes. I'm having a potluck in 10 minutes. So just bring whatever you can in 10 minutes. And then every single person brought the exact same thing. No matter where they came from, they brought the exact same thing. You would think, what? How did you guys talk with each other and all agree that you're all going to bring soda or whatever? Okay, like a 2-liter bottle of Coke. That's weird, right? And this presented what's called the horizon problem. So you can see here that what this is showing is that if we look in one direction, the universe is the same, 15 billion light years as it is over another direction. But yet in the tiny region of time with which this universe had to look like this, only 300,000 years, it wasn't a large enough amount of time to talk with the other parts of the universe. The cosmic microwave background radiation shouldn't be so uniform in such different directions. Something must have happened where the universe had enough time where it was in causal connection with each other, meaning there was enough time for the universe to talk with each other, for light to travel between different parts of the universe in that 300,000 years, or in some tiny amount, before the universe expanded to the size that it is now. And this is the foundation of something called inflation, which is what's represented here as the fact that the universe suddenly just gets really big. And it's the idea that the universe had a period of time where everything could just get to a temperature where everyone was like, oh, we're all at the right temperature we want to be at? Okay. And then the universe expanded quite a bit. And that essentially froze that in place across a much larger region than would otherwise be able to contact each other. And why has inflation worked? Well, that's very complicated. It has to do with spontaneous symmetry breaking. It's very complicated. And I do not want to get into it here, especially because it's 5:51. But when you see a diagram like this, know that Big Bang happens, and then you have this very early on, this inflation, which essentially locks things in place so that it can be smooth on one side and smooth on the other side and smooth on the other side. And then the universe expanded from there, and you get eventually a soup of particles. And so you can see here also, look at right here where it says 300,000 years, 400,000, 380,000 years over my shoulder. This right here looks like the cosmic microwave background. It's because that is representing the cosmic microwave background, meaning we can't see anything before in this region here. From Big Bang to cosmic microwave background, the universe is opaque, completely opaque. Can't see it. Too hot. And then we see what is represented here by the cosmic microwave background. We see that moment. And then from there, the universe is now a bunch of neutral atoms with light just passing through, flying around. And that's what the universe is for 200 million years. For a long time. Or 100 million years, 200 million years. For a long time, the universe is just hydrogen. A little bit of helium. In fact, here, we can look at what the universe is made out of. This is such a good diagram. So this is a diagram that shows all, and I'm so glad I can just stick my head right here between hafnium and barium. This is a diagram that shows all of the atoms we know of, and it shows how we think that they were created. Okay? And so, and in what proportions too. So Big Bang fusion is the Big Bang, is the, I don't know why there's a little question mark by there, I guess because it's an SVG file. Big Bang fusion is the made in the Big Bang thing. And you can see the only things that the Big Bang made at the end of the Big Bang were hydrogen, helium, and a little bit of lithium. That's it. That's the Big Bang made. The Big Bang, at the end of the Big Bang, what was left over from the beginning of the universe was the Big Bang made hydrogen, it made helium, and a little bit of lithium. That's the ingredients of the whole ding-dang-dong universe. I don't know why I say ding-dang-dong. The whole damn universe was just hydrogen, helium, and lithium, with some light, with some dark matter to hold things together, eventually some dark energy. We won't get into that right now. It took a bunch of other things happening, including dying low-mass stars, exploding massive stars, like carbon and nitrogen, dying low-mass stars, and exploding massive stars. Your body is made out of explosions from massive stars and dying low-mass stars, which gave you all the carbon that's in you, right? If you've got gold, here's gold. Merging neutron stars. You have to have 2 neutron stars at the end of their life die to do that, right? Either some low-mass stars you can do it, but generally 2 giant stars have to die. This silver ring I'm seeing right here, which I put next to silver on the periodic table, 2 dead stars had to crash into each other to make that. But we've talked about that. Mostly what I just want to say is that the end of the Big Bang is pretty simple stuff, just all floating in the universe. And the structure that we think that gave rise to that, we can see in this pattern here. So what you're seeing here is essentially like regions across the large universe regions of more dense gas, hydrogen, helium gas. And these are less dense gas. And the question is, well, what happened to that gas? How did that gas do anything? And that's for next week, or 2 weeks from now. That's the subject of 2 weeks from now, where we talk about the dark ages and the beginning of stars and galaxies, which is my favorite thing. But for right now, I just want to do a recap of the universe's history that we talked about by bouncing back over to here. Boop. So we had the Big Bang, We have inflation, which is the origin of fluctuations, where the universe had some little tiny density perturbations, but everything could talk with each other, and then suddenly got really big over a tiny period of time, and then stopped. And then particles formed from that, and more particles than antiparticles, so that we had left over with particles. And dark matter starts building structure. And then it took 380,000 years for eventually the particles that were formed to combine with electrons, the protons to combine with electrons to make atoms that like neutral atoms. And we call this process recombination, which is funny because they were never combined in the first place, so it doesn't make sense why they're recombined. It took 380,000 years, right? So it's a period of time where the universe was this like thick soup of neutrons, protons, electrons just all flying around each other. Eventually it cooled off, right? And the question is, what happened in this period of time right here such that you eventually get stars and galaxies? And that is what we're going to do in a couple weeks. Are there any questions? Because I'm getting hungry. I appreciate you viewing. And if you're viewing here or viewing on YouTube later, I appreciate that. Eight-legged bird and splendid torch here, watching and asking some questions, which was nice. But I recommend Ned Wright Cosmology. It's like old-timey style website, text website. But up here, you've got a tutorial, which talks about the critical observations. Here's Edwin Hubble's observations, and eventually the better version of Edwin Hubble's observations. And the idea behind the universe being homogeneous and isotropic, which we talked about a little bit. The initial fitting of the cosmic microwave background. Here's the temperature on the scale where 0 is black and 3K is white, where you see how smooth it is, right? The microwave sky is extremely isotropic, he says. In every direction is the same. You can also go and look at an Italian version. Introduzione, parte una. I don't know what one is in Italian. And you can watch it, read it in French as well. Il fait de cosmologie. Quelles sont les vérifications expérimentales du Big Bang? Which is pretty fun. You can also look at frequently asked questions, which is really fantastic. Okay, what does it mean to say forces were unified? Does that mean some of the four forces were just more real? No, it means that forces are kind of complicated in that the way that gravity, what it operates on, but the universe was at such a state that the forces were not like what they were. They were one weird force that governed the way that matter moved and interacted with each other, right? Matter being very different at this time, not really being matter. And so it's very complicated. When it comes to the Big Bang, it's very complicated and cosmology. There's a lot of questions about this. I mean, here's a bunch of questions right up above me that are not able to be understood through simple metaphor to it's, gravity operates on these two things, so this is operating on, it's very, very complicated. And I can't exactly answer, but it's not like they were just weaker and there was just one force that was operating above them all. It was just that they were all combined because of how hot the universe was. The way that matter or whatever was in the universe, be it matter or light or energy, interacted with itself was governed by this one force. But if you have more questions or want to go and recap, this is a great page. Ned Wright, you could click on, one of these and go back down. Can objects move away from us faster than the speed of light? Why doesn't the solar system expand if the whole universe is expanding? Does entropy pretend the Big Crunch? What are the value of the Hubble constant? He wants it to be 42 because he's a nerd. I want it to be 69 because I think it'd be funny. It's closer to 70. In fact, it's consistent with 69, which, nice. Cosmology, Religion in Kansas, which is a discussion about cosmology and religion and the state of Kansas. There's a bunch of really cool stuff here and some fun art depicting, hyperbolic planes and stuff. It's a really good website. And there's slides that he's got for colloquy he's given. And he's a really prolific scientist. And I really oh God, what a beautiful image that is. I'm going to end on that. This is Planck data showing the galaxy has not been subtracted out from there. But JR, I appreciate your question as well. I'm going to finish because it's 6 o'clock and I'm getting hungry. But I'll see you all in 2 weeks. I'll also, I think in 2 weeks, do another, the September-October version of the astronomy, of the how to stargaze, which will be fun. Yeah. Otherwise, this was really fun, everyone. Have a nice rest of your evening. Go out and stargaze. Look up some more cosmic microwave background stuff. You know, learn these things. It's pretty cool stuff. Bye, everybody. This is the part where I thank you, Jer, where I kind of sit here and wonder if, you know, people can hear. Stargaze. Okay. Okay, there we go.